All right, so let's continue. So let's look at an example, and it's a standard example in physics textbooks. So you have two objects, two blocks, connected to one another by a rope, and one is on a horizontal surface, the other one is hanging on a vertical, direction. All right, so this problem can give you the surface with friction, or it can be like a frictionless surface. Let's say it says frictionless table, for example. But, technically you can have, let's say either way. Obviously it's easier when there is no friction, but let's say you can, make it a little more complicated or a little more interesting, right, by putting a friction there. So let's say here what we have is this. You have two blocks on a, let's say on a frictionless, where block A is on a frictionless surface, and block A connected to a block B by a string that goes over a pulley. And basically, let's say the system is at rest right now. Basically, you're holding the system right there. Now, imagine then we are using the same idea as we just talked about in part one, which is the mass of the string is massless. That means tension is same everywhere. But also, since there's now a pulley, I'm going to also assume one thing, that pulley is also massless. And this is important because in the later chapters, we're going to learn about if the pulley is not massless, also no friction, that means frictionless and massless, then it just in no way affects the system. That means the tension on both sides is exactly the same. So you can see, right? So there's if you look at block A and free body diagram for block A, you can see, right? There's a tension to the right, normal force up, gravity down. And then here's block B, gravity down, tension up. And if you look at the pulley, then pulley basically can have three forces acting on it. So the tension to the left, tension down, and then there's a friction from the support over there. Okay. All right, so, but if the pulley here is massless, then we can just completely ignore that altogether. And we can say that the forces, the tension, right? The tension as a force is the same everywhere. That means along the entire length of this string, the tension is exactly the same. And all the pulley does is just basically, you just have a string going over it. That's it. All right. So the tension everywhere is exactly the same, which makes our life much, much simpler, to be honest. So you will see in the later chapters when we go to rotational, dynamics, right? That makes, our problem, a little extra difficult. Not something that terrible or something like that, but it's just another step that we have to take. But in this case, what we have here is this. So we can think of like, let's say then since the tension, for both of those strings are both of the object, right? So you have the same tension. That means here's, let's say, tension acting on A, and here's tension acting on B. Those are examples of technically, interacting, right? So interacting action reaction. So you can see, right, this in the diagram, right? You can see right there pretty much exactly the same magnitude. So here's a free body diagram for the block A, which is it's on a horizontal surface. So there's a normal force up, gravity down, and the tension to the right. And what I have here is, then I have block B, where basically it has a tension up and gravity down. This is gravity acting on B, this is gravity acting on A, right? Two different forces, but the tension between them is the same. All right, so I'm going to give you an example where I can break this down even more. But the idea here is this. Because now we have two blocks, so we have mass of A, mass of B, and there's a tension, but it's the same for the entire string. So, and there's an acceleration of the system. That means those are technically the variables in this type of example. And as soon as you let go of the system, then it's, block B gonna fall down, block A gonna be then speeding up to the right. So then the entire system gonna be then accelerating in this direction. Acceleration of A to the right and acceleration of B down. But since they are connected, acceleration constraint tells us that acceleration of A equals to acceleration of B in terms of their magnitudes. So that means that's why I have just one acceleration. I have one tension because tension in the string is exactly the same. And we're gonna see that if you have a system like that, those are the four variables that you will be working with. okay? And, you know, when you do free body diagram and then the force table, you always get two equations. And if I give you 2 out of those 4 unknowns, then you should be able to solve for the other 2. Any 2 unknowns that I give you, any 2 of them that I give you, you should be able to solve for the other 2 unknowns. All right. So here's one example. So we're going to do basically, you know, several examples as, you know, like, let's say, to see how all of those things work. So we start with Newton's, you know, third law combined with Newton's first law, which means that right now we're looking at the system that is in equilibrium. So you say, okay, block B rests on the surface for which the static and kinetic coefficients are 0.6 and 0.4 respectively. The ropes are massless. Good. What is the maximum mass of block A for which the system is in equilibrium? That means you can see, right? So you basically have the system is in equilibrium because the block A has a, you know, the gravitational force acting on it and then the tension. And the tension is the same as this tension. And what you have here is then, you can then assume here is that there's friction force, static friction force that prevents this tension to move the, you know, to move the system, basically make the system accelerate. But obviously what you have is that static friction is fighting against the, you know, this gravitational force of block A. And if it's too heavy, the gravity will win and then, you know, friction cannot keep it, the system then will accelerate. But right now we want to know what is the maximum amount of mass we can have for A so that the system is still in equilibrium. Okay. Now, what we do for that is this. We start by break this down into 2 systems. Okay, system A, system B. And let's look at B first. So let's say for the B, what I have here is the object being at the center. Remember, for the free body diagram, you put the object at the center. And then I look at all the forces acting on it. So, all right, so what I have here is this. There is the gravitational force, so FGB, and there is a normal force, and there's a tension, and then there is the, you know, static friction. So this is my forces for the system B. And if I do my table, so I have tension, I have FGB, I have static friction and normal force. Let's see. Since it's in equilibrium, this is 0, 0. So I have plus T 0 minus, oh, sorry, this is gravity, right? So 0, I'll just write the MBG, right? And then negative static friction, 0, and then 0 plus N. That means what I get here, I get one equation. Equation 1, which is tension minus static friction equals 0. And I get equation 2, which is M, well, remember this was negative, I forgot that. So the normal force minus MBG equals 0. So I get those 2 equations. Next, I do the force table, you know, basically the same thing for the system A. All right, so here's, you know, for A, here's my A, the object at the center. Now let me do all the forces. Well, it has 2 forces only, gravitational force on A and then the tension. So then my force table will be probably simpler because nothing in a X direction. So if I have then tension and then gravitational on A, remember the system is still in equilibrium. So I take T up, positive, gravity then MAG down, right, negative. So I get my third equation where tension minus MAG equals 0. All right, so I get 3 equations. And my goal here is to find what is mass of A. Remember, what I have here is I'm given the coefficient of static friction, and it seems like there's nothing else. Oh, sorry. Also the mass of the block B, which is 20 kilograms. So I'm given those 2 information. I need to find what is then the mass of block B, sorry, block A. I'm given MB, which is 20 kilograms. And I'm given coefficient of static friction, 0.6. Well, we're given both, but we have to understand, right? If you're talking about, equilibrium, we have to use static friction. All right, so now what I need to do here is I need to then be able to combine those equations. So for example, one thing I can see here is this. If I take equation 1, equation tells me that, tension is equal to the static friction. And equation 3, right? So equation 3 tells me that tension is equal to also mass of A times G. That means I can replace tension with mass of A times G. That means those two are equal to one another. But I also know that static friction is coefficient of static friction times normal force. And equation 2 tells me that normal force is equal to then mvg. That means that the right side then here is equal to mu s times mvg, which means then weight of A is equal to coefficient of static friction times weight of B. And that's all basically I end up with. So from here, I can see that I can cancel the G, and then the coefficient, the mass of A is equal to then coefficient of static friction times mass of B, which is 0.6 times 20 kilograms, which gives us 12 kilograms. That means the heaviest that black A can be, right, in order for my system to be in equilibrium, is 12 kilograms. All right, so make sure you guys are okay with everything. Maybe watch it again. And remember, you can always ask me questions during the lecture portion. Let's look at another example. Okay, so this is the one that I told you that, we have a standard, example like this. So here I'm gonna pretty much break it down, everything for you. So you have two boxes that are connected by a cord running over a pulley. So this one will make it a little bit more interesting by having a friction. Then the coefficient of kinetic friction between box A and the table is 0.2. We ignore the mass of the cord and pulley and any friction in the pulley, which is good, right? Which means that we can assume that force applied to one end of the cord will have the same magnitude at the other end. Right? That means tension here is same as tension over there. Everywhere is the same. We wish to find the acceleration A of the system, which will have the same magnitude for both boxes, assuming that the cord doesn't stretch. As box B moves down, box A moves to the right. So that means our goal here is to find acceleration. Now, what we do for that is this. We take and separate this into two systems. System A, which is, here's the free body diagram for that. So you have the force, normal force up, tension force to the right, friction is to the left, and weight of A down. So then let me, use that to get the table for this, system A. So here are my forces. So I have, this is just basically different from the different books. So that's why the notation is slightly different. So F of T is just a tension force. Then let me just put a normal force like this. And then kinetic friction like that. And then this is basically the gravitational force on A. Here's my net force. All right, so what I have here is this for the X and Y, right? So the tension is then plus F of T, 0. For the normal force is just in a positive Y direction. Kinetic friction is a negative X direction, has no Y component. And gravity is a negative MAG. There is no acceleration in the Y direction, but there's the acceleration in a X direction. Okay, so I get that. So then my equation 1 will be tension force minus kinetic friction equals mass of A times acceleration. And my equation 2 will be normal force minus MAG. So normal force equals to then weight of block A. This is my system 2, which is block B. And it only has two forces, gravity down, tension up. So let me quickly do that here in terms of the forces. So you can see, right? It has nothing in the X direction, but in the Y direction. So there's F of T and there's a F of G for the B. Here's a net force. Now here's what I have. The block A was going to accelerate to the right. So I took to the right as positive. Block B going to accelerate down. So I'm going to take down as positive. okay? Just because my acceleration is in that direction, which makes tension negative, and then the weight on B is positive, so plus mvg. And that net force equals mb times A because the system accelerates. That means I have then here equation 3, which is mbg minus F of tension is equals to mb times A. So now I have these two equations. All right, so now here's what we have. You can see that we were given the black A and black B mass, 5 kilograms for A, 2 kilograms for B. And remember what I mentioned earlier, right? So this type of problems, you have 3 unknowns or 3 variables: mass of A, mass of B, acceleration of the system, and the tension in the system. Just F of t, same thing. Which means you have 4 unknowns, and you can assume that the tension is the same for each block, and acceleration is the same because they're connected. Which means then I have just one acceleration, so that's why I didn't put a subscript for then, and there's also one tension, so that's why I didn't put any subscript for the tensions. So now I have then 3 equations, and I have technically 2 unknowns because I'm given mass of A and mass of B, and right now this problem is asking me for me to solve the acceleration. And the easiest way will be to take the 2 equations with acceleration, which is 1 and 3, and add them together, because if I add them together, the tensions basically cancels out. So if I add those 2 together, what I end up here is this. MB, let me kind of put it like this, right? MBG minus F of K equals then MA times acceleration plus MB times acceleration, so it becomes MA plus MB times acceleration. And then I can use this equation, right, to find for the acceleration expression, which will be then MBG minus kinetic friction divided by MA plus MB. All right, and in a way I have everything that I need, because from here I can say, all right, acceleration is equals to MBG minus, now here's F of K. Well, I don't have F of K, but remember, F of K is equals to coefficient of kinetic friction times normal force. That means I can say it's coefficient of kinetic friction times normal force, and equation 2 tells me what the normal force is. This is MA times G. Then this is divided by MA plus MB. And you can see, right, all I need 3 things: mass of A, mass of B, and the coefficient of kinetic friction, and I can solve for that. All right, so 2 kilograms times 9.8, then minus 0.2, then 5 times 9.8, and divided by 7 kilograms, which is their total mass. All right, that means I can use that to calculate basically the acceleration. So then acceleration will be equals to 1.4 meter per second square. Now, I could also have asked you to solve for the tension. So let's say, what if I asked you also to solve for the tension? Well, all you have to do here is this. Now that you have acceleration, you can either use equation 1 or equation 3 to solve for the tension. For example, equation 3 would have been tension force is equals to MBG minus MBA, right? So that's it. Just go ahead and solve for it. So tension force is equals to, you can factor out MB, so just G minus A. Let's say if we do that, I should get 17 newtons. That means I can also solve for the tension. All right. All right, so this is also a very standard example. This is known as an Atwood machine. So you have a 100 kilogram block. An Atwood machine is basically, you have 2 objects connected to one another by a rope, but the rope goes over a pulley such that both of them are in a vertical direction, basically hanging in a vertical direction. And the idea here is this: if mass 1, mass 2 on each side is equal to the same, like equals to the same value, the system is in equilibrium. But as soon as one of them is heavier than the other one, then the heaviest one accelerates down, the lightest one accelerates up, and we call this basically an Atwood machine. Now, let's say taking that, the one of the masses is 100 kilograms, the other one M, which is a little bit, lighter. So what we can have is then the 100 kilogram going to be falling down, the lightest one going to be going up, So then what we have is that 100 kilogram block takes about 6 seconds to reach the floor after being released from rest. And what is the mass of the block on the left? The pulley is massless and frictionless, and we can assume also that mass of the string or whatever, it's a rope, right, also massless. All right, so let's look at this now. How do we, let's say solve this problem? Well, we can assume that, for example, we're given that it's falling 1 meter distance, let's say before it hits the ground, and it does it in 6 seconds. Okay. Now, one of the things we can do with this is, if we know how much distance it travels before hitting the ground, well, we can find the acceleration, right? So I can find acceleration by assuming that since it started from rest, so then V final, so not this one, so displacement delta y is equals to V initial times time, then plus 1/2 AT squared. This equation can be used to solve for the acceleration. This is kinematics equation. Remember, I can always use kinematic equations to find acceleration. And that's what I'm going to do. I can then say, all right, so then since this is 0, because it starts from rest, what I have is this, delta y is equal to just 1/2 AT squared. That means acceleration equals 2 times delta y divided by t squared. So 2 times 1 meters divided by 6 seconds squared. So if I do this calculation, I should then be able to get, the acceleration of the system. All right. So it's basically 2 divided by 36, right? 2 divided by 36. So I get 0.05, or let's say 0.056 meter per second square. Okay. Because it takes 1 meter, it goes down 1 meter, right? And it takes 6 seconds. It's a long time to cover one meter distance. So that's why it's about, it's a small acceleration, 0.056 meter per second square. All right. But now that we have this, then I can use acceleration basically with Newtonian dynamics. Because remember, if I want to find mass, right? If I want to find mass is basically part of those, Newtonian dynamics, Newton's second law. All right, so what we do here, we then separate those two into, 2 systems again. I can say, all right, so here's my system 1, here's my system 2, for example. So this is my system 1, where I have mass M, and it has a, tension up, and then M1G down. So let's call this M1, just in case. So I put it in a table. I can see then, since it's going to be accelerating up, I have then tension, M1G. So the net force will be this. So in X direction, there is nothing there. But in the Y direction, plus T minus M1G equals M1A. Right, so I get that equation 1, which is tension minus M1G equals M1A. Then I look at, system 2, where I have system 2 in terms of mass 2, 100 kilogram, right? So it has 2 forces. All right, so one is the, M2G, the weight. The other one here is then the tension. Okay, so if I'm doing just in the Y direction, right? So let's say my forces. So I have then the tension and then the M2G, right? So here's my net force. So let's say in X direction is 0, 0, 0, but in a Y direction, here's what I have. Again, this is going to accelerate down, so I'm taking down as positive. Means then tension is negative, then M2G is positive, so then M2A is also positive. Okay, that means then I get my equation 2. M2G minus tension equals M2 times A. All right, so what do we do here? Well, I have 2 equations, 2 unknown. I don't know what the tension is, right? But I have the acceleration, and I don't know what the mass of 2 is. But by adding those 2 equations to one another, again, allows me to get rid of one of the unknowns, which is the tension, and then rewrite this equation as, if I subtract, I end up with M2G minus M1G equals then M1A plus M2A. right? Which then gives me, M2G, sorry, M2G minus M2A, because remember, I want to solve for M2, right? Equals to M1A plus M1G. Okay. Now, what I can do from here is I can see that on the right side, I have then M1, A plus G, and on the right side, I have M2 times G minus A. So then what I can do from here, I can then just basically divide, right, those quantities, where then I can say then M2 is equals to M1 A plus G divided by then G minus A. Okay, so if I do that, remember, I am given mass of 1, then I can just calculate because I have mass of 1 and I have then the acceleration. So if I do that, so let's see what we're gonna get. All right, so A plus G, and which is 9.8 plus 0.0056. It's barely anything, right? So, and this is divided by 9.8 minus 0.0056. All right. So, and then this is times 100. All right. So, let's see. All right, so I just realized I'm solving for the wrong thing because I need to solve for the M1. All right, so let me go back here and then, rearrange and solve for M1. All right, so if I rearrange, I end up with this M2G minus M2A equals an M1A plus M1G. That means it's, M1 is A plus G. So then let's say if I then divide both sides, so M1 is equals to M2G minus A over A plus G. So that means this is what I needed to do, sorry. All right, so if we do that, then I should get roughly 98.9 kilograms, so something like that, about 99. That means, the difference is very small between them, right? One is 100, the other one is 99 almost. So that's why it takes 6 seconds to cover 1 meter distance, which is, quite slow. But this is how we would, get that. All right, so one last example. And this one you can think of like, increasing the difficulty of the problem. Because what we get here is we have a box A of mass 10 kilogram rests on a surface inclined 37 to the horizontal. So we're creating an incline. It is connected by a lightweight cord that passes over the massless and frictionless pulley to a second box B, which hangs freely as shown. Well, it's going to be shown in a minute, right there. If the coefficient of static friction is 0.4, determine what range of values for mass B will keep the system at rest. If the coefficient of kinetic friction is 0.3 and mass is 10 kilogram, determine the acceleration of the system. All right, so you can see that this is basically, now we have a system that has, 2 blocks connected to one another, but the surface is not flat for the second one, right, or mass A, but it's inclined. All right, so now the question here is why part A is asking for the range of values for mass B. Well, there are 2 reasons for that, because one thing you can have is this. So if mass A is, let's say, much heavier than mass B, then mass A will slide down, mass B will, move upward. But if mass B here is much heavier than mass A, then mass B will go down and mass A will speed up upward. That means basically you have 2 things. You have 2 cases. Case 1, where let's say the mass of B is such that it prevents from mass of A sliding down, or case 2, where mass of B is heavy enough, but not enough, let's say then, or things like this, the friction, right? So it prevents from mass A from, sliding up rather than sliding down. So like, let's say you have those 2 things. Case 1 is when, you prevent A sliding down. Case 2, you prevent A from sliding, basically sliding upward. That's kind of like then what we have. So let's look at then case 1 first. That means we are looking for mass A to be, sort of like, let's say, such that mass of B preventing, or mass of B is such that, it prevents the mass of A from sliding down. In that case, you can see, right, free body diagram for A, it would be such that you have the normal force from the surface, right? So there's a normal force from the surface. Then there's the gravity acting on it like this. Then what you have here is there's a tension, right, acting. Plus then there's a friction. Because we prevent mass of A from sliding down, then this static friction will be toward, upward, toward where the same as the tension. Okay. Here's then what we'll have for the, like, let's say block B, free body diagram for block B. Okay. Now, using those, since I don't have enough space, I'm gonna, basically skip the force table in this particular example. So we can say that we have equation 1. And equation 1 will be based on, let's say case 1. So equation 1 is for the X components, or the forces, in X. Or let me actually do that, because I want to do that for A, which is, a little bit more complicated. All right, so this is going to be a force table for that. So we have 1, 2, 3, 4 forces. Remember, this is an F of G for A. So let's write down F of G for A. And then I have the tension. Then I have the static friction. Then I have normal force. Okay, net force. Remember, we are talking about static equilibrium. Now, when your system is in equilibrium, it doesn't matter which, up or down you take as positive. So let's take down as positive, like we have over there. That means what I have is this. I have mg, or let me put it like this. It's, the mag sine of theta for the x component, right, of the gravity. And it's positive because it's, in the direction of my positive x. Then minus mag cosine of theta, which is the y component of gravity, and it's negative since it's down. Tension then negative T and 0. Static friction negative F of S and 0. Normal force is 0, then plus N. Then what we end up with is this. So mag sine of theta minus tension minus static friction equals 0. And equation 2 basically gives me then, normal force minus mag sine, cosine of theta equals 0. Okay. Now, system B, which is this guy over here, gives me just one equation. Because if it's in equilibrium, that means that tension minus mbg equals 0. Basically, this is what I get. All right. Remember, our goal will be to do this. We want to, for part A, is that if the coefficient of friction is 0.4, determine what range of values of for B will keep. That means we want to find MB. All right. So then what we will do here is this. I will see that from the equation 2, normal force is equals to MAG, cosine theta. That means normal force is that. Then I can rearrange my equation 1 such that for the static friction, I'm writing this as coefficient of static friction times normal force, which is then MAG cosine of theta. Then this is equals to 0. That means I replaced, static friction with mu s times normal force, where normal force is given with equation 2. Because then I can take equation 1 and 3, right? So equation 1 and 3 and add them together. Just equation 1 and 3. And again, why am I doing that? Well, so then I can cancel the tension. Okay, if I cancel the tension, what I get here is this. I get MAG sine of theta minus mu s MAG cosine of theta, then minus MBG, that's on the left side of everything, right? So then, basically on the right side I have 0, so then this is equals to 0. And you can see, right, that means I have just one term with MB. So I can, move, say that MB is equals to, and here's then what I can do also, which is nice. I can cancel the G's everywhere. Okay. Then MB is equal to then mass of A times sine of theta minus mu S times mass of A cosine of theta, which in a way I can factor out even mass of A like that, right? Okay. So then if I take this and plug in and calculate, so this is, remember it was 10 kilograms, right? For the mass of A. So times sine of 37 minus 0.4 times cosine of 37. Okay, and try to calculate that. What I will get here is 2.8 kilograms. That means 2.8 kilogram is the lowest mass of B can have to prevent mass of A to slide down. All right, so this was for case 1. Now let's look at case 2. So case 2 is basically prevent object A to going, that means, if B is too heavy, it will go down and mass of A will start sliding upward. And what we're saying here is that there's a maximum value of B where we can kind of prevent that, because then this friction here will be strong enough to prevent that. Now, what do we do with that? Well, the only thing changes is then the friction becomes, in the opposite direction from what it was before. That means in my equation, this will be then positive, right? Then this will be positive. Let me do it in red so you can see the changes, right? Then this is positive. Then this is positive, which makes then this guy here is positive, and this is positive. So then this is positive. And if I do that calculation, now with, this new expression, we'll get the 9.2 kilograms. Okay, because we're adding here together. So we get 9.2 kilograms. And that's kind of what we have. Right? That means in this particular example, right, we are looking at the force of friction changing, going from up to right now going down. That means 2.8 to 9.2 kilograms. That's the range of the block B. Okay, that means within that range, right, the system is in equilibrium. Otherwise, outside of that, the system basically accelerates. Okay, now let's do this. Now it says if the coefficient of kinetic friction is 0.3 and mass of B is 10 kilograms, well, what does it mean 10 kilograms? Well, it means beyond the range of, equilibrium, which means that it's not too heavy, right? And it's gonna, slide down. That means, it's gonna basically then, B will be then accelerating down and the mass of A will start sliding upward. That means what I'm saying here is 9.2 was the maximum that you can have for the B to be in equilibrium. But if the mass of B is 10, like we're given in part B, then obviously, you have a system that starts accelerating. So then let's look at that. So what I have here is, am I looking at case 1 or case 2 in this case? Try to think about it for a minute, right? Well, what you can see here is technically then I am looking at case 2 because I have the system now that is accelerating, and then the friction will be then preventing, because now what I have here is the system is now accelerates where B is going down, A is accelerating up, so then the friction will be, but this time is kinetic, right, in opposite direction. The only difference here is the acceleration is no longer 0, so we have then mass of A times acceleration here. That means this is equals to mass of A times acceleration. Okay. Then, excuse me, equation 3 now becomes MBG minus tension equals MB times acceleration. That means here there's also an acceleration downward, taking down as positive, then weight is heavier than the tension. So then we have equation 3 like this. Again, from what we're doing here is, you still have the same equation 1 and same equation 3, and then you again adding those two equations together, because equation 2 just gives us what the normal force is, and I already incorporated that into equation 1. That means now if I add those two equations, 1 and 3, again, what I'm getting here is I get rid of the tension, and my equation basically gives me this. So it gives me then, if I do that calculation, it will be mbg plus mag sine of theta. Oh, never mind, sorry. I have to make some changes here. And the change will be like this, right? See, if now, since the block A accelerating upward, right? If it's accelerating upward, and I'm taking then up as positive, then I can take up as positive, all right? So then gravity here is negative, tension is positive, friction here is then negative. Okay, then I have to incorporate that into my equation. So negative this, positive that, negative this. So this term is then positive. Okay. All right. So now what I need to do here is actually, instead of adding them, I need to then subtract. Well, actually, no. I can just basically add them together, right? Because tension is still positive here and negative there. So here, so I'm adding. So what I get here is this, then mbg minus mag sine of theta. Again, if I add those tensions go away, then minus mu s mag cosine theta. And on the right side, then I have then acceleration times ma plus mb, which means an acceleration equals to mvg minus mag sine of theta minus mu s mag cosine of theta divided by ma plus mb. Okay. Again, plug in all the values, we should get 0.78 meter per second squared. Try to do that on your own. You should be able to get then this acceleration. All right, so remember, so the reason I had to change that, because if the system is accelerating upward, then it's easier for me to take up as positive, so this term is positive. And since gravity acting basically against it, right, and the static friction acting against it, because remember, so for the part B of the problem, we are looking at this, free body diagram for the block A. So that means, the friction and gravity component, X component of gravity acting against the tension. That means tension here is stronger than both of those together. So that's why the tension is positive. Those two are negative, right? And you have a net force in that direction. All right, guys. So this concludes this chapter.